progress.
Good morning. Let us start today's lesson. I would like to talk about the parametrics method for constructing a fundamental solution to the second order partial differential equation of parabolic type. I would like to write down the Kolmogorov backward equation in coordinates form. So we have that equation can be written as follows: d u s x plus the sum over all j from 1 to d a j of sx d u dx j of sx plus 1/2 the sum over all I and j from 1 to d d I j of sx d2 u dx I dx j of sx equals 0. Where Dij are the entries of the matrix of the matrix of dsx. We fix some bases, orthonormal, and our operator. The dsx is the matrix of that operator in that basis, and Dij are the entries of this matrix, and Ij are the coordinates from the coordinates of the vector field ASX. Okay, and we are going to construct such a solution to this equation that is called a fundamental solution. The definition of a fundamental solution is the following one. A function g s x t y of the arguments s and t, x and y.
Sorry, there is a question. B symmetric matrix?
Yes.
Yes.
B, it is symmetric and positive definite. B as x theta. Theta is non-negative because it is the limit. This form is the limit of the following expression: y minus x theta squared p s x s plus delta s dy. The limit this form as delta s goes to 0, this form goes to this expression converges to bs x theta theta, where theta is an arbitrary vector from Rg. Okay? From the point of view of differential equation, this factor 1/2 seems to be strange, because this 1/2 can be included into B, okay? But for a probabilistic point of view, from probabilistic point of view, exactly that function, exactly this matrix or operator is has the probabilistic sense. This is this limit. So let it be that factor. Let it be in our equation. So a function of the arguments s, x, t, y is called a fundamental solution to this equation if it is continuous for fixed t and y as a function of Sx, it satisfies this equation. And for any continuous bounded function phi of x is real values, the following relation holds true. Limit as s goes to t, integral over d g s x t y phi of y phi of y dy goes to phi of x, converges to phi of x for any x in our D. So our aim now is to construct such a function for this equation. Let us consider some examples.
Can you please switch? Yeah. I want to write it down. So this seems a lot like weak convergence.
Yes. This means that this integral is a solution to this equation satisfying the initial condition, in the sense final condition, yes. Okay. Let us consider some examples. Let a function g s x t y be defined by the following integral. Not integral, but the following expression: minus y minus x squared over 2t minus s. Here s is less than t, x from RD, and y is from RD. It was an exercise for you to verify that these functions satisfies Kolmogorov-Chapman equation and it is a density of transition probability that corresponds to a diffusion process with a s x being equal identically to 0 and b s x being equal to identically to an identity operator in G. So this equation can be written in the following form: du ds sx equals plus 1/2 trace u second prime x of sx equals 0. Okay, trace is nothing else but Laplace, the Laplace operator. Okay, this equation is called a hit equation. And you see, if we try to apply Kolmogorov's theorem, so we should verify that the function phi, the f function phi can be chosen about a bounded continuous function phi of y should be chosen such that this function is a function of sx. Okay? Is a function of sx in that domain is twice continuously differentiable in x. Yes? In Kolmogorov's theorem, when we derive this equation, we assumed that this function is twice continuously differentiable with respect to x, and then we assert that it is differentiable also in the argument s, and this equation holds true in the region, in this region. Okay, how to verify that this is true for this example? It is not difficult to observe that dgsx ty dxj is the same that minus dgsx ty with respect to yj. Yes, because the derivative with respect to x is the same as the derivative minus the derivative with respect to y. So if I differentiate this function with respect to x, I can write down this derivative as the derivative with respect to y, and integrating by part, I can write down that this derivative dxj integral gsx ty phi of y dy is integral over RD g s x t y d phi dyj of y dy. So if this function is twice continuously differentiable and its derivatives are continuous and bounded functions, then this function is twice continuously differentiable with respect to x. So we can apply theorem Kolmogorov and assert that this function satisfies this equation, heat equation. This equation is called heat equation. Here is the following detail. We use the following fact that if phi is continuous bounded function, then this integral is a continuous function with respect to Sx in this domain. It is a consequence of the following observation. The function g s x t y is uniformly continuous in every domain of the form S X T Y maybe let us denote it by d delta, where d delta for a positive delta is the set of all these variables such that if t minus s is greater than delta, this function is uniformly continuous in this domain. Why? Because this function is Fourier transform. The result of a Fourier transformation G consider some function h of z that is equal to integral maybe 2 pi minus d integral over rd e to the power I z c e to the power minus c square over 2 dc, and then our function g s x t y is nothing else but h of y minus x over square root g minus s. So this function is uniformly continuous in Z, in all the space or D, and if t minus s is greater than delta, then this function is uniformly continuous in all its argument if t minus s is greater than delta. So we can assert that if this function is continuous bounded, then this function is continuous in Sx. So its derivative with respect to x can be written as this integral, and here it should be written phi prime yk.
So we are assuming that phi is also differentiable.
Yes. In Kolmogorov's theorem was the following assumption: if a function, a continuous bounded function phi is such that this function is twice continuously differentiable with respect to x, okay? If now I can assert for this function that if phi is twice continuously differentiable and be such that all those derivatives are bounded, are continuous and bounded, then this function is continuous. If I write down here phi prime or phi second prime, okay?
Sorry.
I can use Kolmogorov.
In this representation, G in the representation G by H, there should be some, I think, T minus S before H, because in J there is T minus S before the exponent.
No, you see, here is in G is this.
Change of the variable.
If I change variable in this integral, then I obtain this expression. Okay?
Okay, thank you.
I have one more question about this. So the problem is in the point t, right? So because t minus s
Yes,
approaches,
yes.
but it seems to me that this function approaches 0, and there shouldn't be a problem in the point t when s approaches. But the exponent goes to 0 faster.
And if x equals y,
Yeah.
If
I
x
see.
equals y, you have singularity.
We can say about all the points y, x in RD. Okay.
Yes, yes, yes.
And h is just characteristic function of h is characteristic function, yes?
Yes. Yes. H is a characteristic function of a Gaussian, of a normal distribution in RD. Okay. So you see, we can apply here Kolmogorov's theorem and assert that this function, if phi twice continuously differentiable and is bounded along with its derivatives, then this function is a solution to this equation, and initial condition is fulfilled also. Okay, but here in this situation we can immediately verify that without any differentiability assumption on this function is a solution to this equation. Why? Let us calculate the derivatives of this function. dg ds sx t y. We have differentiate this expression with respect to s here and here. So the first one, minus d over 2, and minus here, d over 2 t minus s. And the derivative with respect to this s we will obtain minus and it minus y minus x square over 2 t minus s square, and this must be multiplied by g s x t y. Okay. Now let us differentiate this function with respect to x. dg dx j s x t y equals xj minus will be plus 2 yj minus xj over t minus s g s x t y. And the second derivative, d2 j g dx I dx j s x t y equals derivative of this function is minus delta I j over t minus s. Okay? And derivative, the derivative with respect to xi gives us one more multiplicator of this type, y I minus x I over t minus s squared. Now, if I consider the sum over all I from 1 to g, d2 g dx I squared,
We should just multiply by.
oh yes, yes, thank you. Multiplied, must be multiplied by g. Okay, so if I equals j and the sum, maybe let us write that. Let us write the following: delta with respect to x, g, s, x, t, y with 1/2. You see, plus d dds equals 0. You see, this 1/2 and the sum equals this and 1 with the opposite sign in this. So you see that this is a fundamental solution to the heat equation. Then A equals identical 0 and B equals identically an identity operator. Because this function is continuous in all its argument, okay? It is uniformly continuous in the region d delta for positive delta. So it is continuous in it is continuous in all its arguments, and it remains to verify that integral g s x t y phi of oi converges to phi of x is t minus s goes to 0. But this is a very simple assertion, because this integral can be written as follows: phi of x plus y square root of t minus s e to the power minus y square over 2 dy over 2 pi to the power g over 2. And if phi is a continuous and bounded, it is very easy to see that this goes to phi of x as t minus s goes to 0. So this is a fundamental solution to the heat equation, and our aim is now to construct such a solution to the general equation of this type. I am going to consider now some properties of this function and its derivatives. Maybe let us make a break, a little break. I am going.
Recording in progress.
I'm going to investigate some properties of some estimation. I would like to obtain some estimations for derivatives of this function, and something like these questions. But firstly, I would like to consider the following. So we have the following problem. We have just see that a solution to maybe Sx plus 1/2 delta with sub x means that operator delta acts on this function as a function of this argument x. U s x equals 0, and u, this is true for s less than t. T is fixed okay, and x from Rd. And the initial condition, initial in the sense of final, equals phi of x. This is a Cauchy problem. This is the Cauchy problem for this equation with this initial. And a solution to this problem can be written in the following form: integral gs x t y phi of y dy. If phi is, for example, bounded continuous function, then this is a solution to this equation. And now let us ask ourselves, what about non-homogeneous equation? If I write down here some given function f of s and x, so we have here two given functions. One of them is phi, initial function, and the second one, f s x, is given for s from 0 to t, x from Rd. They both are real valued. Okay, and if f equals 0, then a solution can be written in this form. And what about a solution to this problem, non-homogeneous, when here is written a function different from 0, so we call this problem non-homogeneous, this equation non-homogeneous, and it is well known from mathematical physics that a solution to this problem can be found as the sum of two functions, one of which we denote by v as x. This function satisfies this equation with 0 on the right hand side, and it satisfies this initial condition. And
Recording stopped.
And the second function, w s x, must be such that it satisfies this equation and 0 initial condition. Okay? Then the sum u v s x plus w s x will be the solution, will be a solution to this non-homogeneous Cauchy problem. Okay? So we have to should try to find out a function WSX that satisfies this equation and 0 and initial condition with 0 function. Okay. Let us write down the following integrals. Integral from S to T, d tau, integral over RD, G, S, X, tau, Z, F, tau, Z, dz. Okay. I would like to formulate some assumptions about the function f tau z, such that this function is a desirable. WSX is given exactly by these integrals. So, let us consider the derivative dw ds of sx. We have that s is here and s is here. If I differentiable this integral with respect to this s, I should receive the integrand at the point tau equals s. So I should find out the limit of this integral as tau goes to s, integral of RD, G, S, X, tau Z, F, tau Z, dz. Okay, and plus integral over ST d tau, integral over RD, dg ds, sx tau z, f tau z, dz. I don't know yet. Is it possible to write down this derivative in this form with respect to this argument? Okay, but I formulate somewhat later some assumption on function f that allow us to write down this derivative here. But one of these terms is here, and I forgot to write down here minus, okay? Because this is the lower.
Excuse me, do we write the limit as tau approaches s, not just
what if you have some integral from s to t c of tau d tau, and if you take the derivative of this integral with respect to s, what is it? It is integrand at the point s. So if this function is limit, is continuous, so this is the limit.
Okay. So we just need to write this as a limit.
Yes,
We will use this later.
we have to calculate this limit and justify the possibility to write down this derivative under the sign of the integral. Okay? Okay. And if we suppose that this function is continuous and bounded, for example, yes, so we see that the first term goes to minus, this limit is equal to minus f of tau x. Okay? Because that integral under the sign of limit can be written as integral e to the power minus y square over 2 f of tau y, not y, x plus y square root of tau minus s dy over 2 pi to the power d over 2. Okay? This is the integral under the sign of limit. Okay, and it is evident that if tau goes to 0, then, and f is a bounded continuous function, so this goes to f s x. Okay, so the first term here is equal to minus f tau x. And now we have justify why this derivative, why this integral exists, is well defined.
Minus f s, right?
S,
Not
S, thank you, S. Minus f s x. Now let us consider this integral dg ds. You see, this dg ds, dg s x ty tau z ds can be estimated as some constant
Recording in progress.
t minus s to the power minus d or d plus 2 over 2 e to the power minus mu y minus x squared over t minus s, tau minus s, tau minus s. You see, we have here exactly such a term, but here now is equal to 1/2, and here we have y minus x square over t minus tau minus s square e to the power minus y minus z minus z, I'm sorry, z minus x, okay, z minus x, z minus x square over 2t minus tau minus s. And tau minus s to the power minus d over 2. 2 pi. Okay, and now you see I can, for any mu positive and less than 1/2, I can write down the following inequality: z minus x square over t minus s over tau minus s e to the power minus z minus x square over 2 tau minus s is less than some constant e to the power minus mu z minus x square over tau minus s. Okay? This is inequality of the following type: x for positive x, e to the power minus 1/2 x squared. X is positive now. It is less than k e to the power minus mu x squared. For any mu less, for any positive mu less than 1/2, we can choose a constant k that this inequality is true for all x, for all positive x. I use here this inequality: z minus x square over tau minus s. This is x. Okay, so you see this term tau minus s to the power 1 remains here, okay? So it gives us the multiplicator tau minus s to the power minus 1. Okay, and here we have tau minus s to the power minus 1. So this derivative can be estimated this way with some constant. It depends on d and mu on mu, but it does not depend on s tau zx. Okay? And now I would like to draw your attention to the following circumstance, that if I write down this integral ds, okay, f tau z dz, and if I try to estimate it in absolute value and write down here integral over rd, absolute value of this derivative, and absolute value of tau z. So this integral is not well defined, because you see we have here not this integral is well defined, but we should integrate them with respect to tau, and this is impossible, because you see we have here integral. I can continue this inequality. Norm f this is the supremum of this absolute value of this function with respect to tau and z. Norm f, this integral is a constant, some constant, multiplied by tau minus s to the power minus 1. And I cannot integrate this function over this interval, okay? So only boundedness of the function f is not sufficient. But fortunately, we can use the following circumstance. I know that integral over rd g s x tau z dz equals to 1, x equals 1. I know, so integral over rd, the derivative, equals identically to 0. Therefore, I can write down this derivative, integral from s to t d tau integral of RD dgsx tau z ds, and here let us write down f tau z minus f of tau x dz. This integral is equal to this one because this integral is equal to 0. Okay? I subtract here 0. And now, if our function f is such that it satisfies Helder condition locally in x uniformly with respect to tau, it means that f, suppose that f of tau z minus f of s x locally from z minus x is less than delta. For any x, let some delta positive exists such that this difference is less than some constant c z minus x to the power beta with some positive beta. Beta and c can depend on x, but not phi tau x. You see, phi tau z, f tau z minus f tau x. Tau, this estimate is fulfilled for all tau. Constants c and beta may depend on x, but they are not. They do not depend on tau. Then this situation is much better because here we have locally this estimation, and now I can write down the following. I can calculate the derivative of this integral by the following formula: minus f of s x plus the integral over RD dgs x tau z over ds, and here we write down f tau z minus f tau because this function under this condition is such that this integral exists. Why? So we have already seen that this integral can be estimated in the following way. Integral over s over the interval s t d tau integral over rd e to the power minus z minus x square over 2 tau minus s no
The estimate was mu.
estimated that let us write down absolute value here, and here we write down the estimation mu minus mu tau minus s tau minus s to the power minus d plus 2 over 2, and here f tau z minus f tau x dz, and we write down this integral as the sum over b delta of x, and here I can use this estimate, okay, this estimation, and I receive z minus z here, z minus x to the power beta, okay, and I can once again use that inequality, z minus x to the power beta over tau minus s to the power beta over 2. Let us use the following estimate mu z minus x square over tau minus s to the power minus d plus 2 over 2, and z minus x to the power beta. We write down here tau minus s to the power beta over 2, and here I should write down beta over 2. Okay, and now I can write down that this is less than some constant e to the power minus mu tilde z minus x square over tau minus s, and tau minus s here we obtain plus beta over 2, and this is exactly what we need, because now when you integrate this over that ball, we must obtain tau minus s to the power minus 1 plus beta over 2, and this integral is well defined. This is estimation of this integral over the ball b delta of x. And as for the complement to that ball, tau minus s z minus x is greater than delta, so there is no problem in estimation that integral. So we have the following formula how to differentiate this function with respect to s. The same reasons can be applied for the second derivative with respect to x of this integral. So we have that dw ds sx plus 1/2 delta w s x equals minus f s x if f is a function with the following properties. It is bounded, continuous, and is locally and satisfies locally Hilbert condition as a function of x, uniformly with respect to s. So this is a solution to non-homogeneous Cauchy problem. Okay, and it is easy to see that Wt minus x equals 0. Okay, because if function f is bounded, so this goes to 0 as t minus s goes to 0. So I would like to write down the result. Our result is this one. If we have the Cauchy problem du ds of sx plus 1/2 delta x u s x equals minus f s x s t is fixed and u t minus x equals phi of x. Then the solution, a solution to this Cauchy problem can be written as the sum of two integrals. One of them is g s x t y phi of y dy plus integral from S to T, the tau integral RD G S X tau Z F tau Z dz, under which conditions on given function f, phi and f. Phi is a bounded continuous, f is a bounded continuous and satisfies the Hölder locally, the Hölder condition in this argument uniformly with respect to S.
Excuse me.
Yeah.
And we don't need to write this minus f tau x because this will give us 0, right?
Yes, because this equals to this integral. This function is not
Independent of
integrated with respect to z. It does not depend on z, so this integral equals 0.
Okay. Yes, we can just omit this. Mhm.
And the same concerns not only derivative with respect to s, but the second derivative with respect to x, because the s is equal to delta g, okay? So the second derivative of this integral with respect to x can be calculated by the similar formula, but there will not be here term, yes, and here we should write down delta x. So, okay, thank you for your attention and see you.
May I ask a question?
Yes.
So could you please summarize what is the parametrics method finally?
This is not final. This is only
Okay.
only start.
Okay.
Yes. I will explain next time.
Okay, thank you.